So we're in the middle of studying these scale invariant solutions to the spherically symmetric Einstein scalar field system. So unfortunately, I have to start by writing quickly the equations again. Um, so let's. All right. So remember our basic unknowns. We're getting very used to this at this point. Are the function r, the laps, the scalar field, or we have the wave equation for the function r, plus dr u dr dv equals minus 1/4 omega squared. We have the two, these are the Ricciarduri equations, or the null constraint equations, which you can think of them as ODEs for the think of them as ODEs. The most natural way to think of them as ODEs for the function r along that go along null hypersurfaces. But it's sort of amusing. Yeah, sometimes it's not that you only use them to study r, of course. But anyway, we'll in fact see that. All right, and then you have the v version, which is just that we replace everything. We can always swap u and v everywhere. All right, and then we have the okay, and then we have the scalar field equation, which is the wave equation for phi. All right, and I'm not going to write out the equation. So then the null lapse also has a basically a wave equation it satisfies. I'm not going to write it because we're not going to use it. And I wrote it before. All right, then we also had various scaling relations that we were using. Let me write those out. So all right, these are the equations, and then so under self-similarity, we have u du v d this equals r. Um, this equals 0, and this also equals 0. Um, all right. Okay, that's that. And there was one thing that I forgot to say when I was introducing the hockey mass last lecture that's kind of just important when thinking about the hockey mass. So remember, we have this hockey mass. So we have this hockey mass M, which, well, in this gauge satisfies um -4. So I talked about this as hockey mass. I referred to a useful rigidity property that if it vanishes, the solution's flat in a certain region. We talked about that, but what I didn't, and then I also separately talked about the concept of a trapped surface and how, basically trapped surfaces, you should think are related to future null infinity being complete, though I didn't discuss why at all. That's just a black box fact. All right, but then I didn't put those together, which was the whole point of that little digression, which is that you can easily read off if you have a trap surface from the hockey mass. So basically, you have a trap surface. So UV is trapped, if and only if this is negative. All right. And if you ever forget what this should be, just think about Schwarzschild. So, well, I guess you have to remember Schwarzschild, but hopefully if you study relativity, you have the Schwarzschild metric memorized. And there's this 1 minus 2 over r that when that switch is signed, that corresponds to moving into the black hole region. And so, you know, anyway, this relation, that's how you can remember that relation. All right. So any questions before we get going? All right. All right, so I guess I'll probably just leave that board like that. All right, so then we were in the middle of this first part. So what we're doing now is we're studying such solutions. We're trying to find them. So um, so we sort of start by assuming we have such a solution, maybe deriving things that have to be true about it, and sort of um, uh, eventually we'll end up with some explicit things. So like I said, um, so we started from. Oh, maybe I should give these numbers. That might be useful. 1, 2, 3, 4, uh, 5, 6, 7. All right. Actually, I'm not sure that we even use this equation, but it seems important. But not using some equations is related to what I mentioned, of course, that these are very overdetermined, right? They're three unknowns, but they're five equations and also extra scaling relations. So, it's not weird that we don't use a lot of the equations. Okay, so the starting point was we started with 2 and 3. I won't write this out because we did it already. And then so we took 2 and 3 and we used the scaling relation 7 and so from seven what we used was um we used this, which is the consequence of 7. And we also used uh so 5. All right. And what we did before was we combined well, we did 5 and also we differentiated with du or dv to get a version of 5 from the relation for 5. You can also get some things for second derivatives. All right, we combined. So we used 2 and 3. We combined them with some weights, used these relations, and we ended up with the following. And we got the following equation, which is where we ended last lecture. So we had dr du minus v squared dr dv. All right, so we had derived this equation. Okay, and now I just said in words that last time what ended up happening is that we're going to conclude that the lapse is has to be constant. So the point is, so now what we can do here is we can write this right as u dr du and u like this, and then use so this so we can use 5 and 7 to replace these quantities with their v versions. And yeah, so what happens? You get I do mean 5 and 6, thanks. All right. And here it's very easy for me to mess something up. So um the key is I remember my very first math instructor in college told me that sometimes it's very important not to think too much. So I think this is one of those. You just have to just plug and chug. All right. So we're gonna get minus v dr dv plus r and minus v d omega dv and um then we have minus v squared dr dv equals 0. Yes, that looks good. All right, so then these ones, right, will cancel with those, right? When the v's when these hit each other, and so this implies that well VR. Okay. All right, and again, everything is we always can exploit that everything's symmetric with u and v. At least in not everything in relativity, but this particular context that we're in. And so similarly, All right, you can basically, instead of replacing these with the relevant equations, you replace the other terms, and you will conclude that you are. All right, and we know that. All right, so R vanishes only at the we're always work with spacetimes where there's remember one time-like curve where they're the fixed point. So R is not zero in the spacetime. So we can divide by R, and then U and V we're also working well, U and V might be zero, can be zero, I guess, somewhere. But um let's nevertheless draw the conclusion from this that therefore omega has to be a constant. All right. Where we're sort of suppressed, omega jumping at U equals zero, B equals zero. All right. Okay, so that's nice. Let's continue. Let's check for questions. No questions?
That U equals zero and B are what makes one identical, so everywhere else is conflict.
Well, I mean, you can say that. But I made this whole big point that we're not only studying smooth solutions, right? And so in general, the solution of v d lambda dv equals zero. Well, I mean, you can still get to this, right? So I mean, I just didn't want to say it all. But so v d lambda dv equals zero, then that should mean that in general you're a delta function at v equals zero plus a constant. Then this would mean you're a delta function at u equals zero plus a constant. So well, you can't be a delta function. I mean, you can't be both a delta function of v equals zero and a delta function of u equals zero. So you conclude it has to be a constant. Exercise, if you want. Okay. All right, so then let's continue. So all right, so lambda has to be a constant. All right, but moreover, we can I guess I'll leave this. Moreover, we are free. So there's an underlying, so we're looking for, so remember our metric has this form, du dv plus r squared. Right, this and we have the scaling symmetry, right? We have that u du plus v dv. This maybe I don't know what I called it before. This thing is a conformal killing field, right? Meaning the Lie derivative of this. Well, I mean, meaning those things. All right. So there's an underlying, so metrics which satisfy this, there's some symmetries that we can do. Basically, we can rescale u and v, and it will all be okay, right? So for example, so if I do a change of variables, like if I replace u with a times u, or let's be more precise here. So if I say u tilde, right, is a times u, then of course then d by du tilde equals d by du times a inverse, right? And then so what we see is that this will equal u tilde over a times a du tilde, right? These things will cancel. So this, all I'm saying is that this structure, the fact that this thing is conformally killing, which, and how it generates in those corresponding relations is invariant under, for example, a simple rescaling. So if A is in, I can always do a rescaling like that and keep the form of everything, keep everything the form. And similarly with V. So in view of that, I can so because of this, but if you look about what happens, of course, when I do this, I'm going to get, well, so in this case, I'll get this times A inverse, right? So what you see is that I still have a self-similar solution in these coordinates, and but I have the freedom to get this constant out here. So the upshot is if I can do such a rescaling, and then I can make the lapse actually just be a one. I can normalize it to be one. All right, so the upshot is after coordinate rescaling, we can assume that this is just equal to 1. Okay. But we do have to remember one thing, which is that we used up that freedom to rescale the coordinate. All right, so that means that from now on, so once we've done that, from now on, so from now on, now the only things that we're allowed to do, we can do a u tilde equals AU if we simultaneously do a v tilde equals a 1 over AU v. So we still have that freedom. We can do that. But we cannot just scale one coordinate anymore. Okay, so that's nice. We got rid of the labs. Any questions? Zoom? Nope. All right, cool. Okay, so now let's keep going. Ooh, that's the. Okay, so now let's go to the wave equation for R. And I claim that we can rewrite this the following way. So I claim that R d squared R du dv plus dru that this. And these are these things where if my notes are wrong, it's not good. Hopefully they're that this is equal to 1/2 of du dv r squared. All right, let's maybe check that. All right, so if I do one derivative, I get, say, du dv, right, of r dv dr. All right, this looks promising. All right, okay, so, and we know that the laps, all right, so I'm just saying that the left-hand side of the wave equation for R can actually be written as a, sort of a normal 1 + 1 dimensional wave equation for R squared, right? Which is nice. Why is that nice? Because it's really easy to write down the solution, the general solution to a 1 + 1 wave equation. So given that the lapse is identically 1, so since the lapse is equal to 1, we have that let's just write it. Yeah, so if there's the 1/2 there, there's the minus 1/4 there, we end up with d squared du dv of r squared equals minus 1/2. All right, so this is kind of, so there are a lot of, in a way, there are a bunch of miracles that occur in the ability to write down this class of solutions explicitly. So you think the first miracle is that the lapse has to be, that there's just rigidity here, that the lapse is constant. Second miracle is that, this R function satisfies extremely simple equation. Means no, a priori, no reason for that. Okay, so now we know from our, from PDEs that to write down the general solution to this, even allowing for weak solutions, right? And we know that, so with this implies that, so R squared has to be equal to 1/4. And I'm trying to use here the notation from Christodoulou's paper, 1/4 some function of u. So in general, right, the solution is a function of u plus function of v. We have this inhomogeneity, so we have to also include a term for that. So we have this, and then we have, because of the 1/2, we get minus 1/2 u v. All right, all right, so that's, if we didn't have any scaling constraints, that would be the general solution, or where these are some function of u, some function of v. Okay. Yeah. And all right, but we also have the homogeneity constraints. We have this from 5. And we know in general that R, well, the different ways to say it, but we know that R of, well, since this is squared, we know that r squared of AU AV for any constant A has to equal A squared r squared of UV, right? So that imposes constraints on what these functions can be. And so the upshot is the following. And yeah, I have to stay on these boards. I guess I'll just go over here.
Wire function, it's like written like O plus and O minus.
That's just, I'm following the notation that Christodoulou used in the event that you want to look at that paper. I don't know why. The plus and minus, I don't know why he did that, yeah. I guess it's a theta, yes, but yeah, I don't know why. Yeah, you could just do like theta one, theta two. I don't know. But, here's my thing. All right. Yeah. So now, so by um so by homogeneity, we have some constraints here. So what we can do is this theta plus of u, and so here I'll just kind of tell you the answer. If well, let me say what this is first. So we know that it has to basically theta plus has to be like a quadratic function of u. It has to have this scaling, right? It has to be a homogeneous function of u. So but which I claim means the following. So we can write it as c plus plus u squared when u is positive, or c plus minus u squared when u is negative. All right, where c plus plus and c plus minus are, well, at this point are just our constants, our real constants. Okay. So again, now why does it have to be the same? Why is it allowed to jump? Right. That's the same when I did the case of the spherically symmetric wave equation. I did that. I tried to do that slowly. And we saw there that when you're allowing these weak solutions, when you cross when you cross uh u equals 0 and v equals 0, there was this ability to make these changes. So, I'll just say exercise, workout. In this case, this is what you're allowed to do. You're allowed to have this function. This constant can jump, right? Right, and then theta minus v has a similar thing. And again, let me just make sure I said I'm trying to follow Christodoulou's notation here. So he called this that c minus minus v squared for this is for v less than 0, and c minus plus v squared for v greater than or equal to 0, and we're again now c minus minus and c minus plus r and r. And here at least the pluses and minuses um correspond to the signs of those things, so that makes sense. Okay. Yeah, anyway, that's that. Let's quickly just so eventually this stuff becomes second nature to you, but in case you're still a relative newbie to thinking about U's and V's, let's remind you. So if we in the usual, so here's the UV plane. We don't yet know that where the solution actually will be defined, but let me just remind you, right? So so here we have, this is U less than 0, intersect V bigger than 0. Here's U less than 0, intersect V less than 0. Here's U greater than 0, intersect V greater than 0. All right. Just if you're thinking about. So what happens is, so this solution, we're allowing some kind of uh jump in the second derivatives of our squared as we go here, and then another jump in the second derivatives as we go here. Great. Questions? No. All right. Check Zoom. No questions. Cool. Then let's keep going. All right. Okay, but all right, so just as a solution to the wave equation, that's sort of all you could say. But of course, it's not just a solution to the wave equation. It's the
I have a question.
Oh yeah.
Why theta for B is continuous from the right, while theta plus is continuous from the left? There's a reason for this, or
From the right,
why
from the
why
left.
you're taking the inequalities?
Oh, it doesn't make a difference where I put it, right?
Okay.
Because they're both zero there.
Ah,
This was just, I don't know, for some reason in my notes, I wrote it that way in my notes for some reason. But yeah, yeah. No, well, it's silly to write it that way. Um, all right. So like I said, so if just in terms of it being a solution to the wave equation, um, that's all there is to say. But of course, it's we have to remember that there's a geometric object here, and r squared, like for example, r squared is positive, right? Well, no, we'll get there. Yeah, yeah. No, I haven't said that all of these work. That's exactly what I'm saying. They don't all work. This is just from it being a weak, a weak solution to that inhomogeneous linear wave equation. We get that, but immediately there are more constraints because r squared should be positive, for example. So let's we won't do that all at once, but let's look. For example, um. Yeah. Okay. So let's look at v equals 0. So let's look along. So here's the first thing that we're going to do. So let's look along v equals 0. All right. So in this case, we have oh, I probably should. Oh, there. Okay. R squared. Well, I guess I guess it works. All right. So r squared at v equals 0. This is going to be equal to well, you'll just get the u one. Well, r squared at v equals 0 is just the one that's negative. So you get 1/4 c plus minus u squared, right? So in particular, this better be true. Um, okay. We can solve for that. So we get that. So r at v equals 0 equals 1/2 square root of c plus minus. Let's write it minus u. Because remember, so I drew this picture. So on v equals 0, u is negative, right? So that's the right way to write it. Okay, some further things that we can look at. We can also examine, we can compute. So just by differentiating that expression. So by differentiating the formula for r squared at v equals 0, and then at v equals 0, we find the following thing. So we get 2. So when you take the derivative, for example, in v, so you naturally on the left-hand side see get from the chain rule, you get 2r dr dv. The u part goes away, and then in the so the u part goes away because it just depends on v. The v part is quadratic in v, right? So also the derivative, you won't get anything if v equals 0. So you're just going to see minus 1/2 u. Right, and then you can do similar thing. You can do 2u dr. You can also look at the u derivative, do the same thing. So now on the u1, we're going to get well, there's a 1/4, this is u squared. So and it's negative, so you get it's so easy to write the wrong constant. I think C plus minus U, that seems correct. And the V you don't see. And then when you take the derivative of this last term with respect to U and you evaluate if V equals 0, you get nothing. All right, so you get, anyway, these are all, it's tedious, but you get this. Okay, so let's putting that all together. So then, so keeping now in mind, so from, oh no, sorry, did the wrong one. All right, so if we look at this and this and this, these ones will all imply, so here, here, and here, if you put all of those together, what you're going to get is that dr du times dr dv at v equals 0 has to equal, I claim, 1/4 because some reason. Right? Because so what you do is you write this like that and plug in all the formulas. All right. And then so this equals that at v equals 0. And then if you work it out, you get minus 1/4. So this constant scales out. Okay. And what is the, all right. So I guess that's okay. I mean, some of these, there's always this thing it's unclear to what level there's a point to doing this, but I don't know. There's the other extreme where you don't ever do anything. You just say the answer. But somehow I think it's interesting here, like that that you can do it is very weird that this works. So that's why I thought it's interesting to do. All right. So all right. So okay. So why did I make the point of that particular computation? Well, because now you can notice something, which is nice. Which is we can look at the hockey mass now. So remember, I have this formula for the hockey mass. So now I have that 1 minus 2m over r. So let's do this at v equals 0. That has to equal minus 4. Remember, the lapse is 1. And then I just computed that dr du times dr dv is minus 1/4. So all these constants matter. So this is 1, right? So here I use that formula for the hockey mass. And so this implies that the hockey mass along v equals 0 vanishes. Okay, and that's a very useful fact. Does everything make sense? Yeah. All right, so that tells us, so remember at the hockey mass, I told you had this very nice rigidity property. It's always non-negative. And then if it vanishes somewhere, you draw the picture, you draw the sideways triangle and the side, to the axis. So, well, let's draw this picture. So here's, again, we don't know, I'm just going to draw the biggest possible region that our sort of space-time could exist. We don't actually know what's going to happen yet. But, all right, it's saying that, so here's v equals 0. And it's saying if you have a v equals 0 in your space-time, basically, then what we've concluded from all of this, after doing just that rescaling to make the lapse 1, is that the hockey mass has to vanish along this line. Right, so the hockey mass is vanishes here. And to that, remember, so if you vanish there, remember it tells you that you draw something here and you have to be flat in that region. All right. But of course, I mean, it vanishes on this whole thing, so I could do that everywhere. So the conclusion is that I have to be flat. So the solution must be flat in v less than 0, and the scalar field must be constant. That's a result. That's a consequence of this rigidity that I said before. All right, and moreover, it's not just that like some abstract geometric statement, that it's flat. I explain it's because of these these are things that are way harder outside of spherical symmetry. But in this like rigid spherically symmetric setting, um, this thing is flat. You understand exactly the gauge ambiguity. It's not just flat. It's it looks like usual in Minkowski space up to rescaling the v coordinate or rescaling the u coordinate just by function of u or v, right? Um, okay, so that's kind of nice. Um, and it turns out that you can do basically sort of if the solution exists, um, at u equals 0, which we don't know. It's kind of strange that you're able to do this analysis without even having we haven't solved for the scalar field or anything, right? This is all just based on the R function. So if the solution existed at u equals 0, then it's usual. Like I said, in this system, the u's and v's are all symmetric. So everything solution must be, maybe I say solution is maybe kind of a weird way to put this because the whole thing is the solution. I should say space-time. The space-time must be flat there. So in here, the space-time must be flat for and the scalar field constant for u positive. All right. So if the solution exists up to here, it must be flat. All right. And the scalar field's a constant. All right. And also we can by translation, so because we can add a constant, we can add a constant to phi always, right? That doesn't so um so without loss of generality, let's assume phi is 0 when. All right. And so now this is amusing because it starts to be very similar to that spherically symmetric wave equation situation that I did at the beginning, which if you remember what happened there was exactly this thing that we checked that the solution was a constant here, some stuff happened here, and then was a constant here again. So it's like, and it was like some kind of and there was a derivative jump there for the scalar field. So it's like from the derivative jump, some energy shot in, and then it kind of bounces perfectly and all goes out. So what you see is, okay, we don't know what's going on here. We don't know if the solution exists. And in fact, or just getting ahead of myself a little bit, there will be settings in which it doesn't exist up to u equals 0. We'll see that. But at any rate, what you see is that, I mean, it's evocative of that. There's some non-trivial geometry starts here, and it's like it shoots in and going, and then bounces perfectly and comes up. It's pretty remarkable that even in this simplified system of after imposing spherical symmetry, it's pretty remarkable that some structure like that is still there. Yeah. All right. Other questions?
Just thinking about nuclear and that's by switching U and
Yeah.
that.
Yeah. And again, I mean, if that sounds too fuzzy to you, you can literally repeat all the arguments. So there's something in the chat. Is UV equals 0, 0 on gamma something we assume or something we derive? So far, I haven't made any. This is all in the event that that gamma is defined there and that the solution exists. So, I mean, yeah, if that. So I've made no, I mean, all of this, every time I make a statement so far, it's conditional on the like region of space-time that I'm studying that it's there. But I mean, so far, though, I should say, having said that, right now, what we've done is we've concluded that if the space-time basically exists up to v like at v equals 0, then the only thing you could put here basically with the center is something flat. Okay, but on the other hand, I mean, something flat does exist. Like, so so already at this point, I mean, we certainly have a solution always up to v equals 0. I mean, it's not a very interesting solution. We put something, you could just put the Minkowski metric here, the flat metric here, and put the, like I said, and make the scalar constant 0. So we have that. We don't know anything more. All right. Any other questions? No. All right. Just X that out. Doesn't add, but there we go. Okay. 351. All right. So okay. So next thing, let's use our final subboard. I brought this down. It's up here. So we have one final rescaling freedom left to use. So we talked about, so I rescaled one null coordinate so that I could make the lapse 1 without loss of generality. I have another rescaling I can use. So let's go ahead and use that. All right, so let's use our final freedom to rescale. So remember what we're allowed to do now is send this to, AU, A inverse V for some A, for some positive A. And so what I'm going to do is I can use that to make, where's my thing? I can use that so to make that coefficient be 1 there. So I'm going to use this. And we know, of course, when we do, well, I mean, this is the formula for the rescaling, so you can see how it affects R. And so I can do such a rescaling. I can do such a rescaling so that C plus minus is 1. But now I have no more, I can't play around with my null coordinates anymore. Okay. And so, all right, and then this will sort of imply, so then, and soon will be a natural place for our mid-lecture break. And so now this implies, so now exercise, you want? Okay, so from the flatness in V equals in this region, the fact that if we take C plus minus to be 1, and if you, I mean, I guess I've erased it by now, but this, okay, so if you remember, so there's this function of U and this function of V. So remember that, so you have this, there's this guy, and this one has, this is C minus minus V squared when V is less than 0, and C plus minus, no, sorry, minus plus V squared when V is greater than 0. So remember that, so we have this flatness in this region. And again, like I said, it's not just an abstract geometric flatness. It's concretely, we know the ambiguity in the coordinates. So if you go and you look at what I said and look at the formulas we have for R and the fact that this is 1, what you'll find is that C minus minus has to also be 1. So C minus minus has to be. Okay, so the upshot of this is that we've normalized our coordinates so that it's not everything, and we've used this freedom to add a constant to the scalar field so that really it's exactly Minkowski space with a 0 scalar field in this region. So in V equal, so basically here, it really is the case that G equals minus du dv plus, this standard form. And, all right. But we've used up all of that fixes our UV coordinate system. Remember, this is what I think, unless I messed up some. It's always easy to mess these factors up. But I think R is 1/2 V. I think because of these lectures, I'm finally remembering now. R is 1/2 V minus U in my convention for V. Of course, people have different U and V conventions, but in my convention, R is 1/2 V minus U, so R squared is like this. All right, so this is what it is in V equals 0. All right, so that's, I guess, a natural place to take our break. So let's take a 10-minute break. So let's start at I guess 4:06. All right, so let's get going. So there was some question in the chat, but it seems like it was answered successfully, I think. Yeah, everything's resolved there. Okay, cool. So let's keep going. Oh wait, I said 4:06. Oh, it is 4. Oh, different. Now it's 4:06. All right. My iPad disagreed with that. All right, so where were we? Yeah. Okay. All right. Yeah. So we said to this region, what's the last thing I wrote? Oh, the last thing I wrote was here. So then I should move this board up. Okay, so like we said, so this U, the region where U is bigger than 0 is flat. And we've sort of just had a bunch of discussion about how it doesn't mean that you can write the coordinates in this form, but there's still a lot you can say because, based if you look at that rigidity statement I gave you, we know exactly, there's still lots of constraints on what it can look like. I mean, it has to look like, this up to some changes of variables, which are consistent with it being scale invariant too. And sort of one thing that comes out of that. So in U greater than 0, flatness will imply the following. So if you want, again, I mean, I don't know, I could almost everything I say, I could put the label exercise. But so if you want, and then this is that, oh my. So C, yeah. So basically, so C plus plus, so that's the coefficient of R squared, the U coefficient of R squared when U is positive. So C plus 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 times C minus plus, which is this, or maybe I can just remind you. So this was C plus plus U squared when U is positive, and this is 1, right, when U is like this, right? Um, right, yeah. That these have to be 1, right? You can assume that they're both 1, but they have to multiply to 1 based on, this is okay, exercise based on what we know about R, what we've determined so far about R and the fact that it's flat. I mean, this certainly has to be true. Remember, we have this formula for R squared, and the cross term is minus 1/2 U times V with no coefficient. I mean, that's related. It's sort of, so they have to multiply to make that cross term UV. Okay, that's fine. So now let's finally go. So now let's look where all the action is. Let's look again, and this is also if solution exists. If the solution exists. All right, so now let's look in the region where the action is. Okay, so here we can you can do a little computation, right? So again, we have this formula. So 2 times the Hawking mass over R. This, because the lapse is yeah, so I'm using this thing up here. Because the lapse is 1, I can write that as 1 plus 4 dr du dr dv. And I can do, so I have the algebra worked out. Maybe I'll spare you this. Yeah, I mean, I don't know. It's not that hard. It's just, all right, you just plug in so we have this formula for R, we have all these coefficients, and if you just work it all out, you get a pretty a nice compact formula here. You get that this is equal to C plus minus minus 1 times U V over 4R squared, right? Right, so wait, is it C plus minus the right one? Doesn't look right. No, it should be C minus plus probably, right? In the paper, that's a good sign. Yeah. It doesn't make sense, different than the paper. That's like, good evidence. Okay, anyway, you get this. So you work that out. Okay, and then, okay, so again, so keep in mind that we still haven't all of this stuff is conditional on a solution existing. We're trying to sort of, it's still not clear that we're going to be able to, understand anything, certainly explicitly and even not just explicitly. But just sort of trying to get constraints. One thing that you can see from here, so remember, I told you before that if you have, a space-time with this regular center, that the Hawking mass has to always be non-negative, right? You think of it like some kind of energy. So we know that this has to be true. And and U is negative in this region, V is positive. So the upshot, so this implies a constraint on C minus plus. So this implies that C minus plus has to be has to be less than or equal to, well, let's say less than 1. If it's equal to 1, then the Hawking mass is just 0 everywhere, and we're going to get just Minkowski space, right? Okay, so we must have this. All right, and so now we introduce this parameter. So we introduce a parameter k squared, parameter k, so that C minus plus equals 1 minus k squared. It's a bit unfortunate terminology because there'll be another very important k from another paper of Christodoulou that means something different. But okay, again, in the event that you're looking at his paper, let me use that. Questions? No, we're good. Okay. Okay, so that's nice. All right, and so the upshot is that we have all right, so then we can write now that 2m over r therefore equals minus, well, maybe I can write it like this, k squared times minus u v over 4 r squared. All right, in this region where something non-trivial is happening. All right, this formula also tells you now immediately that as long as k is not 0, that there is non-trivial geometry. Again, in the event that the solution exists, that it will have to be non-trivial. All right, so that's nice because it would have been quite annoying if we just got Minkowski space at the end. All right. Okay, and then non-triviality again is just like the case for the wave equation that we looked at, the spherically symmetric self-similar wave equation. Yeah. All right, and so yeah, we can also can be useful. So now we sort of have explicit formula. So now we have kind of explicit formulas. So because okay, so now we've just introduced a parameterizing the C minus plus, and we know that well, this one is 1, this one is 1, then the other two have to multiply to 1. So everything, all of the kind of the geom and the lapse is 1. So all of the geometry just comes down to this function k, and it's all through what the function r is in terms of u and v. So we can write that. Okay, so this we already have that. So when v equals 0, we know that when v is less than 0, sorry, we know that r is this, right? And then here we have well, this formula, r squared equals 1/4 u squared plus 1/4. Well, you can already see, well, some things. At least when this is actually positive. At least when this is positive. Right. So already if that expression does not define something positive, then that's an issue. And yeah, and then let's say so you can tell, so if k squared is less than 1 in some region of u greater than 0, so using this, where did I write it? Oh, this thing about them multiplying to 1, you can see that you're going to have, if you work it out, that you have to have this. Oh, this is, well, yeah. All right, again, well, yeah, when this is positive. All right. Okay, so that's those are just some formulas that you're able to understand things in terms of that. Okay, but we still don't know the scalar field. All right, and then so now to go to the scalar field, well, we use something sort of amusing. Like, so I mentioned that so I wrote down this this equation 4, but we're not actually going to use equation 4. Well, I mean, at some point I'm just going to tell you what the solutions are. But actually what we're going to do is we're going to again go back to 2 and 3, which are, remember, these are the Ricciarduri equations. And these equations, so because we know, well, the lapse is 1 and we know exactly what r is, I mean, at least in terms of some choice of this k. What we have, so we, we have assuming all that stuff, assuming it all makes sense and all that stuff on the left-hand side is positive, so I can take a square root of it. We have, we have a formula for the gradient of phi. And so indeed, if you work that out, so from So from 2 and 3 and the formulas we have, you well, basically, again, let me spare you the tedium of deriving it. Again, and this is all in the region where things are non-trivial. So u less than 0. We have d phi du has to equal kv over 4 r squared. And if again, it's everywhere, there are non-trivial chances that there's a typo in my notes. So anyway, you end up with that. Okay. And all right, where again, remember r is, we know exactly what r is. Okay, so now okay. And then I guess you might think, well, I don't know how obvious that is to solve given the formulas for r, but if you're Christodoulou, you can do it. So is that, I always forget my board ordering. I think I'm here now. I don't know. Doesn't matter, maybe. All right, and it turns out you can just write down this. Again, note that this is because there's no topology in the UV domains we're considering. There can be up to adding a constant to phi. There's a unique solution to this, right? And we've also already well, somehow we already used up the ability to add a constant to phi by making it 0 before v. So if you can just write down something, then that's the right thing. So of course you can just try to do some integrals, but I'll just tell you what the answer ends up being. So here's what you got. So okay, so when v equals 0, we always have that phi is 0. And then now in the interesting place, so when well, in general, so when v is bigger than 0, then you get at least where this is well defined, you will have the following. Okay. And then well, if k yeah, so if k is less than 1, then in u greater, so remember in u greater than 0, that's that top region, everything is flat and the scalar field is constant. So basically, of course, this formula might cease to make sense before, depending on what these values are. We want to plug in, u equals 0. But you could have some issue here before you get to equal. Oh, I'll write out all the cases in a second. But if this is less than 1, then you will exist up to u equals 0, and then this formula will make sense in that this whole region. And then we know that to the future of u equals 0, you're frozen at whatever the constant ends up being. So you're going to get phi equals 1/2 of log. The v's will cancel, right? And you're just going to get 1 minus k over 1 minus k. All right, and again, it's just you can just check that this solves it again. All right. Okay, so then it turns out that so basically the upshot is we get 3 different situations. And I guess there's a final thing, which Christodoulou doesn't really discuss so carefully in the paper, but he says so sort of these are the formulas. So what you can do is you can check that they're various. We didn't even use the equation for the lapse, the wave equation for the lapse, for example. But you can't. Well, of course, the lapse is just 1. So it's not that it's a difficult equation to check. But you can go and actually check that all the equations. We really use 2 and 3 very heavily, but you can check that 4 is true. We also use 1. We know 1 is true, but you can check that 4 is true. But some sense, the way we've presented it, you do have to check that. It's not right. Okay, so all right, fine. So now we did this work, and sort of remarkably, we're able to get these explicit formulas, and that's nice. So now we can kind of interpret. Let's try to physically or mathematically interpret all the things that we found. Okay, so there are basically 3 cases of interest. So there are 3 cases that all behave very differently. 3 cases which behave differently. So you can see that everything is I should have maybe emphasized this, but k is always bigger than or equal to 0, right? Because I introduced that parameter was a k squared there, so everything is invariant. I can just assume without loss of generality k is positive in all these formulas. And I should have said that before. I've used that k was positive. Okay, so you get three cases. So basically, well, you could sort of imagine there's k squared less than 1, which is sort of related to when you end up getting to this region. There's this sort of strange, there's some transitional thing that happens. I'm going to draw the pictures for all these in a second. And then there is when this k squared is bigger than 1. And you can think of these as somehow, so remember that k equals 0 is just everything is Minkowski. Right? If you if you look at all the formulas, you'll get k equals 0, then the scalar field will be 0 everywhere, all the geometry is trivial. So as we're increasing k, we're like making a more and more of a large kind of probing large data in this restricted setting more and more. And so we'll see a key transition will occur around k squared equals 1, where then some stuff will happen. And it's interesting to interpret that stuff. Okay, so maybe I'll pause. Questions? Yeah. Chat's okay. All right. All right. So yeah, so k squared less than 1. So this is the regime where you can think the solution behaves like the linear wave equation. Behaves like linear wave equation. So that is to say, so it's all defined everywhere, right? So you have this u equals 0. You have this v equals 0, right? So we've already drawn this picture. So here, well, let me just draw the scalar field maybe. So here, because somehow the scalar field is the most important object in reality. Because remember we introduced the scalar field because if you have no scalar field, then there's this rigidity and you would just have to have Schwarzschild. So in some sense, scalar field contains the meat of, well, I would say the scalar field and the Hawking mass kind of contain a lot of information. And then, all right, and then we have this, right? So then we have this. Right, and then we become this constant. Okay, so yeah, so it's kind of like it's like the case of linear wave equation. So this k sort of corresponds to roughly the like strength. It's like the strength or the size of the derivative jump of the jump, in if you just look of dv of phi as you cross. And if you remember, there was a very similar thing in the case of the linear wave equation, self-similar wave equation on Minkowski space that we had. So there, we had nothing going on here, and then when you cross v equals 0, we had a one parameter family of things we could add in that corresponded to the derivative jumping. There was a constant a, and then I got confused between a and a tilde and all that, but forget about that. There was the strength of this jump, and here, if you can check that k, so when k is 0, then phi 0 goes to phi 0. There's no jump, and then as you increase k, this jump is getting bigger, right? But as long as k squared is not too big, then so some stuff happens, and then you get to here, then all the action stops, the derivative jumps again, and you become constant. And you can kind of see that as k is going to 1, the size of the kind of, even though it's a constant here, the size of the displacement is getting bigger and bigger, right? So it's kind of, but it's a very good analogy. I mean, it's as similar as you could hope with actually the case of the linear wave equation, which is interesting. Makes sense? Yep. All right. Okay. So I should say in particular, no reason to call that a naked singularity, right? Uh, uh, there's no sense, this point, okay, obviously it's a low regularity solution, so there are various things that are singular, but there's no, again, I tried to emphasize this point that we're interested in, for cosmic censorship, we're interested in singularities which arise from, sufficiently regular initial data. It's up to you to decide what sufficiently regular is, But certainly, whatever you work with, if you want to call something, the singularity that emerges needs to be worse than what you started with, or else it's kind of silly, right? And in this case, so we have, there's some jump here. There's no sense that anything ever gets worse. In fact, it kind of looks like very symmetric. Yeah. Um, okay, so that's that. That's the k squared less than one case. Yeah, maybe again, it's there, but I'll just say it again out loud. I mean, so the scalar field remains bounded everywhere also. That's one thing. Okay, so oh, there was another thing, I guess. You can, well, all right, it's fine. I'll just leave it. All right, so now we can look at, so what happens when k squared is exactly equal to 1? Well, in this case, basically, you this region will not exist. So now the picture, so you're going to have, uh, yeah, how to put it? You'll have this u equals 0 here. So we still have this is our gamma. So here's v equals 0, right? So again, scalar field is 0 here. And then, so now the scalar field is equal to 1/2, right? Log of, of, um, of u minus 2v over u. And so as u goes to 0, we have a logarithmic blow-up. So the scalar field is now going to infinity as u goes to 0. So this you can think now is like this is fair to call sort of a genuine like singularity, and that the again, I'm being very loose with this. I mean, you can get more sophisticated in these discussions. But let's just say, I mean, certainly, the scalar field is bounded initially, right? So the fact that it's blowing up at u equals 0 is sort of, you could at least, contemplate the claim that that was a worse singularity than what you started with, right? Because before the derivatives jump, but the scalar field was bounded. All right. There's some other things that are interesting about this. So you can also check, if you look at, I've erased them all, but if you look at the formulas for the R function, then what happens is that, so on this hypersurface, so as R approaches this thing, it's actually equal to 0, which is which is strange. So it's like so there's a sense, yeah, I guess I didn't get into it, I didn't explain it to you up there, but no, u equals 0. So this is u equals 0, this is v equals 0. No, this is R, the scalar field. Sorry, yeah. The scalar field will always vanish if v equals 0 because it has to be continuous. So it's always 0, and then the derivative jumps. Yeah, and so I'm trying to understand this. I'm saying the solution only makes sense up to here, and I'm explaining like the geometry of what's going on at that point. And so first of all, that the scalar field is going to infinity, but what's sort of strange is that the area of the spheres, if you lift it upstairs, the spheres are actually totally collapsed. So it's kind of, and so you can sort of, I mean, it looks a little weird because you would think, is this like a continuous family? Like what happens, But this kind of thing happens all the time in like geometric PDE because everything's about coordinates, and the point is, you know, and I won't give you what time is it? 34. I won't give you the formulas here, but so here, because this is the normal Minkowski space, so here u equals v, right? But here u does not equal v on this thing, right? At no point did I ever introduce that requirement. That's easy. You might think, oh, near the axis it should look like, the normal circle, but it doesn't. So u is not equal to v there. So there's some range and you can work it out. Well, you can look at Christodoule's papers. You can even work it out from the formulas I gave you for R. Remember, everything everything only is valid, until R becomes 0, and then that's sort of the gamma. So, there's some range of U and V, and sort of that's why somehow, and again, remember, like, we draw these diagrams, these Penrose diagrams. These are all some conformal, whatever. It's kind of I'm allowed to, anything that's time-like, I can do it, it's reasonable to draw as being straight up and down until the second that it's null, and then then I'm not allowed to straighten it out. So this picture looks a little, anyway, exercise, think about that maybe. Ask me. Yeah, so that's a good exercise to understand how is it that I had a whole flat region here, so I drew it like this, but then there, all of a sudden, it ends at a diagonal thing. All right. Okay, so that's what's going on there. So you can already ask here, this is kind of, so like I said, one of the motivations, the main motivation I gave for looking at this is trying to find naked singularities, though I think already sort of anticipated things by saying we will fail to find naked singularities here. But so if you were trying to think about it here, you could get excited, right? So we have some data, we get a singularity. So the question is, is there an incomplete future null infinity? But for that to even make sense, of course, you need somehow things to be asymptotically flat. But even before we worry about that, in some sense, we can sort of just stop before we even get started, because whatever is going on out here. Remember this picture of a naked singularity that we have. This is the idea. There's something like this. This is some singularity, right? There's the light cone of the singularity, and then there's future null infinity out here, right? So the idea is no matter how far you go out, you travel finite time, you hit this. Well, because R equals 0 here, that kind of suggests to you that it's going to be, even if you try to, there are things you can do. You can try to modify the spacetime over here, glue something in, do whatever. But, I mean, here, whatever future null infinity is, definitely R equals infinity at future null infinity. I mean, it's an infinity, right? Or R is infinity. So there's basically like no chance that you could make this, whatever the global geometry of the spacetime is actually very weird, but I'm saying, like, you don't even need to start thinking about it, because this already tells you it's probably not going to be useful as a model of a naked singularity, because the singularity is at R equals 0. And the whole thing is R equals 0. So even if you think that this is going to hit, I mean, it can't hit normal. It's not going to be this naive picture, certainly. All right. Okay, nevertheless, it's a weird object. It's an interesting object that's on a transition. It's the first singular object in this family, and that's kind of interesting. All right, but naked singularity is probably not useful, because the singularity, it's all 0 radius, kind of. Okay, so that leaves the final situation, which is k squared bigger than 1. Let's go here. All right, so now, well, you might guess that now the solution won't even exist up to u equals 0. It'll break down before that. So I'll draw the picture, and I'll just give you some formulas. So what happens, so now when k squared is bigger than 1, you get the following sort of situation. So you have, so here's 0, 0. Here's your fixed point. You always exist. Remember, you're always flat here. Phi is always 0 here. But then what happens is that you have a singular boundary, which will be some space-like thing, maybe call B for boundary. So this thing will be sort of the endpoint of your space-time. This curve will exist at here. So B will be when U is equal to, this is just I copied the formula from the paper correctly, will occur when u is equal to minus k minus 1 over b. Again, this just, right. I mean, this is not some mysterious thing. I mean, it's just when that log function blows up, right? You're just looking when the denominator and the log goes to 0. And so that's, your scalar field is going to blow up. So, and again, so phi is going to go to infinity as you approach B. All right, but there's something else interesting that happens, which is that there's also a curve. We'll call this is a curve A, and this A is going to be it's going to be given by u equals minus k squared minus 1b. So again, because k is bigger than 1, this, if you work it out, this occurs before this one. And what happens on A, so A is in a so-called apparent horizon. So A is an apparent. All right, so this is when the spheres are exactly transitioning from being not trap to trap. So on here, you have that 1, so 1 minus 2m over r equals 0, exactly, on A. And then in between, so in between A and B, 1 minus 2m over r is negative.
And we didn't have this region A. in this case.
In that case, yes. What? Oh, Ava, I wrote something. Yeah, at u equals 0. Yeah, I mean, it's weird because because r is equal to 0 there. So, yeah, well, I actually I wrote something. So at u equals 0, what follows from the formulas is that so if you take the limit as u approaches 0, so from below of 2m over r, this will equal 1 half. So in particular, 1 minus 2m over r remains positive. So you don't have, so yeah, actually I should have, it's a good that you asked, because that's a sort of interesting point. So sort of you don't have this apparent horizon here. That's why you might get excited, because I told you that trap surfaces are these things that protect you, from, so you might have gotten excited that that's not happening here. So it's an singularity. But I said, but then the geometry of the singularity sort of precludes it from. Again, that's not a proof, right? I mean, this is like a heuristic that it'd be hard to modify this to. Why does this not work? Okay. Yeah, sorry about the video. Okay, so now we have a kind of awkward amount of time. But no, but it's okay. All right. So yeah, so we'll continue. So what I'm going to start. So next on Wednesday, what I'll talk about is so there's this. You can think of this as a failure if you want, but actually these solutions were quite important for Christodoulou and a theory he built, though not for finding the naked singularities in some sense, for a different reason, which I'll explain in 2 seconds. But he also was interested in finding naked singularities. And for that, what he did was he introduced a more complicated version of self-similarity, which is sort of a little, this is kind of, I tried to emphasize, this is the most naive kind of definition of a self-similar solution you could come up with. But there is a more complicated thing you can do, which is related to the fact that you have this extra, there's not just this rescaling symmetry, you also have the symmetry where you add a constant to the scalar field. And so you can try to sort of couple the normal rescaling with the ability to shift the scalar field. And this leads to some more complicated type of self-similarity, which Christodoulou studied in a separate paper. And then these class of solutions, they're not going to be smooth still. They'll have this kind of, they won't be C2, but they have a geometry that you nevertheless can interpret as showing, as being a naked singularity. And we'll go over that on Wednesday, we'll do that properly. But I want to say one more thing about these solutions, which is interesting, is that, okay, so having written all these down, one conclusion is sort of that this. So remember, Christodoulou calls these types of self-similar solutions scale invariant, and so we use scale invariant to distinguish because there's this more general notion of self-similarity I'm going to introduce later. So kind of one of the upshots of this analysis is that the scale invariant solutions behave nicely actually. So you have, when they're small, they have this like linear behavior. And then even when they're large, they have singularities, but the singularities do exactly what they should. So it's kind of these are some, yeah, they're nice. And so this kind of inspired Christodoulou. So what he did was he built a functional framework as kind of proofs of kind of well-posedness theory for the Einstein scalar field system, which is in a sense based on these, which I can. I mean, the whole story is very complicated and not really the topic of this course, but let me just briefly say what I mean. And then I should say this paper where he writes down these solutions, that's the main point of that paper, is proving a well-posedness theory for the Einstein spherically symmetric Einstein scalar field system in the certain function class, which he called solutions of bounded variation. So let me explain. All right, so Christodoulou was inspired. Well, I don't know. Maybe I shouldn't think what inspired him. But Christodoulou built a a functional framework for well-posedness around these solutions. Okay, what do I mean by that? So well-posedness meaning, so this is, so you have some data, there always exists a solution that's unique within that class, and the suitable sense might be complicated. There's continuous dependence on initial data. All right, some version of that. Okay, and so he called these solutions of bounded variation, which is somehow confusing because it makes you think that the scalar field is a bounded variation, but that's actually the derivatives of the scalar field are a bounded variation. Okay, so roughly speaking, so very roughly, you know, what does it mean for a space-time to be in this class? All right, so it's a bit complicated. You can look. I mean, at the end of the day, there's not really a substitute for diving into that paper. But so I'll just tell you about the scalar field. So for the scalar field, basically, first thing that you require. So if in a region where your solution exists and is a solution of bounded variation, one thing is that all of the when you integrate on, let's say, so u equals constant hypersurfaces. So u equals constant. These are where v is increasing, right? These are outgoing ones, and along that. So one thing is, so you take a soup over all these ones. So if you're a solution of bounded variation in some region, then the soup over all these hypersurfaces in that region should be finite. And there's always the analogous. So v equals constant du of phi. All right, so this is one condition. So some things to note about this. So note that these are scale invariant in the sense. So if you take your v coordinate and you replace it with a times v, this integral doesn't change, right? This is this thing in many PDEs that there's like this some intuition that it's it's great if you can try to establish well-posedness in some kind of space which is invariant under natural rescalings of the equation. Now sometimes you can't do that, sometimes you can. There could be different ways to do that, but often that's a useful thing to do. So these are scale invariant. Under, u goes to AU or V goes to BV, right? Okay, but that's one thing that you require. Yeah. Oh, maybe another thing to say about this. And so what's interesting about this actually is so just if you think about just scaling and how with this with these scale invariant solutions. So remember, the scalar field has like I introduced this terminology like scaling weight zero, right? In that you can write this as, some function, say, of v over minus u. Like there's no power outside. And then remember, when you take derivatives, the heuristic is you decrease the scaling weight by 1, right? So just based on scaling, the derivative of, for example, the derivative of phi in the region, say, where u is less than 0, should be of the form, minus u to the minus 1 times some function of v over u, right? Let's write it like this. Okay, and so I just want to keep that in mind when interpreting these things. It's kind of interesting. So this says when you go along, sorry, maybe, let me do this one. All right, so this says, in particular, say, for example, when you go at v equals 0, right? You get this, right? So if this constant is not 0, then this thing will logarithmically diverge, right? So it's kind of these kind of norms, are invariant under this rescaling, are naturally associated to this rescaling, but because of certain logarithmic divergences that are not allowed, they don't include like the generic object that scales. And again, what's interesting, you can go back to all these solutions, and for example, here, this thing will satisfy that du of phi at v equals 0 equals 0, actually. So all of these scalar fields are, well, it's because they're constant here. They're constant along v equals 0. So in particular, their du derivative actually vanishes there. So they do satisfy this. But this, you see, just to give some idea of how the sense in which these are embedded in this framework. So that's one way. And then some other things, yeah. So you also need more regularity than just the derivative. So where's the actual BV thing is that so this theory also requires that R dV of phi and R du of phi are BV functions. BV functions. Again, and you do this is this thing when you study, it's very common and kind of geometric treatments of hyperbolic equations that you always, you don't work with spaces that are really isotropic. I mean, you look at derivatives and the, you look at the derivative and you look at norms that are on the hypersurface, kind of the characteristic hypersurface where that derivative is tangent to. That's the natural thing with hyperbolic equations. So again, so here you're going to make that R dV is required to be BV, and this is again along u equals constant hypersurfaces. So the BV norm of this should be the soup of all of these in your region where your BV, that should be finite. And this should again over v equals constant. And so what else do I want to say about this? Oh yeah, another thing, I'm running out of time here, but so another thing, maybe which again can be motivated from this. So again, so if you're BV, if your solution is again this so-called BV, then you also require that M, the Hawking mass over R. So remember, so the Hawking mass, well, if you remember the Hawking mass is scaling degree 1, if you could trust me. So remember the Hawking mass is like 1 minus 2m over r equals 4 this dr du dr dv. So these things are all scaling 0. This is a constant. So m over r is scaling. I mean, more importantly, m over r is scaling weight 0. So if you are invariant under scalings, then you expect that this is, some function over u, right? All right, so in other words, this is a scale invariant quantity. In the same way that these norms are invariant under rescalings, this is a quantity which you kind of might think it doesn't see the scaling. And one of the things that you require when you're BV is that m over r should go to 0 as you approach your fixed points, gamma, the axis. Again, you always only care about along null hypersurfaces. That's very, very important. Right, that's another well, I'm just giving a flavor of this thing. And again, you can sort of see that from these solutions. So these solutions, we had this formula for I think, remember the Hawking mass was like, what's it? K times minus UV. Maybe I forget, there's a 4 or something like this. There's some expression like this, right? And so again, I mean, look, right? When you approach the origin, which is where everything non-trivial is happening, if you approach it along u equals constant, along a u or v equals constant, then it has to be that either v is 0 or u is 0. And so this condition certainly is satisfied because m over r is 0 on those things. It's related to why it was flat above and below. If you tried to approach it sideways, on a space-like curve, so if you tried to go like here, then that's not gonna, it won't go to 0. It has some number. But again, this whole function space is always based around only looking at these characteristics. Okay, and it's a whole kind of complicated story. But is there anything else I want to say about that? Yeah, not really. I mean, there are various. I'm leaving. Obviously, I can't do full justice to this. There are various boundary conditions also associated with this class. But anyway, so he built this while posing this on it. I guess the final thing maybe to say just in the last minute is that what he showed is that so you can, with data just satisfying, some the scalar field satisfying things like this and the R satisfying some corresponding conditions, you always get a solution. And where that solution exists, it has, it will have, so where that solution has a regular axis, you can pick any point on that axis, some u naught, v naught. You can always, translate everything to, well, yeah, you can always, translate everything to make that 0, 0 if you want. And then you can do a sequence of rescalings around that point. So you can then look at, uv goes to, oh, then always the question is it going to infinity or going to 0? Right, so you want, so -1. Yeah, so for lambda going to infinity, so you can do a sequence of rescalings like this to any solution that comes from this theory. You can look at the axis, any point on the axis, do a sequence of rescalings like that. And what he proves is that this will always converge to one of those solutions that we wrote down. So that these kind of really, so this is a precise sense in which these things I wrote down are like the model solutions for this well-posedness theory. And so in that sense, it played an important role for Christodoulou, even though, because he worked in that function space later, even though they weren't examples of naked singularities. Okay, so we'll end there, and on Wednesday we'll start talking about this more complicated self-similarity and give an overview of how Christodoulou used the geometry of those solutions that Christodoulou studied. All right, any questions? Nope. All right, then I'll end this.